We're going to look at this concept called logarithmic properties. And I'm going to also call these identities, which is the correct word, but all book call it properties. As we have discussed before, there's no equation attached to the logarithmic function. And having said that, if you take calculus, you will see that there is an equation attached. However, this equation has infinitely many terms, which means you could not write it down, the actual equation. The equation, however, does contain a pattern for each term. So what it's done is you describe the pattern. So just a little bit here. So this would be similar to saying, write down what the square root of 2 is. X square root of 2, all best I can do is approximate it, but this is a irrational with infinitely many terms that never repeat. So if I want to describe the square root of 2, I do this. If I want to describe the log of log base 10 of 3, this is log base 10 of 3. Okay. This also is an irrational. It is a number that never ends and never repeats. And again, what I mentioned here about the function of logs, true of other functions in other settings. Something must be programmed to the calculator to produce an answer when one types, for example, log of 5. So there is something attached, but we can only approximate it. So algebra is known for manipulations of expressions and equations to get them in a certain form. The entire point of function notation f of x equals y is to communicate an idea to the others. Cannot emphasize enough the importance of this notation. And why am I saying all this? Because I'm lining us up for what we're about to do. So this section deals with identities. No book calls these identities, but if you take trigonometry class, that's exactly the name used, not properties, but identities. The functions used in trigonometry are of the same family type as log functions. They have no infinitely written equation, no finitely written equation attached to them. Instead is an equation of infinite terms. So let's figure out a couple things. And we'll look at the product rule. But first, before we look at the product rule, what is an identity? The product rule for logarithm is a property of or identity, whichever word you decide to use. We use these identities to solve equations or manipulate expressions so we can recognize or act upon some process. But the question is, what is an identity? So here's what an identity is. An identity says that two expressions are equal for all values in the domain. This means that one expression can be replaced by another expression. For example, does x minus 4 equal 2x plus 1? Does that depict an identity? So what I'm going to do is I'm going to treat each one separately. So when I look at this one, here is this equation. Okay, and again, the domain of this is all reals. I'm going to recognize that, right? And when I look at this other one, the domain of this is also all reals. Okay, but are they equal for all values in their domain? So if I want to replace this with a 7, is that one also the answer to this one? And you can see clearly no. What if I, for example, replace x equals to 7, here I'm going to get x, 7 minus 4, that's equal to 3. But replacing the 7 on the other one, I get something entirely different. I get 15. So no, they're not replaceable. They're not the same thing. So literally an identity says these two are identical for everything in their domain. That's not true. As a matter of fact, this only has one solution. If I were to solve this, I would find one solution. So they're not the same thing. So these are not equal for every value in the domain of both these functions. What about this other example? Does 2x minus 12 equal 2 times x minus 6? And again, same thing when I look at this function. SC domain is all reals. And when I look at the other one, again, I get the same thing. Domain is all reals, but I'm thinking visually you're recognizing something immediately. That when I look at this function, and then I look at this function, I realize that if I distribute that too, I get exactly the same function. In other words, I replace this with a 3, replace it with a 3, and I get the same result, right? So if, for example, if x equals 3, then what I get is 2 times 3. Again, I'm not sure why I'm doing this. You can see that it's going to come out exactly. I mean, it's literally the same equation, right? So it's the same. So are these two identities? Yes. These two functions are identities. And that seems pretty obvious. And again, when we massage or manipulate, we're creating identities every single time. That's the whole point of when we manipulate algebra expressions, we're trying to create identities. So this seems kind of weird since that seems obvious. So what is it that we're about to do? Well, let's look at that.